Organometallics are incredibly important, and so we're going to talk about both of these things. One of them is the Grignard, which I know looks like it's spelled Grignard, but it's actually a person's name, so be sure you say Grignard, like this is an N-Y, instead of a G-N. So it's Grignard, which has to do with magnesium and a halogen, often bromine. And we also are looking at organolithium, where we have a lithium connected to a carbon. So let's talk about first about how these guys form, and then we'll talk about its reactivity. So for a Grignard, probably what we have is some kind of alkyl halide, maybe ethyl bromide, for example, in solution with some bats. The bats are flying around. The bats are any kind of ether. I'm just being silly. Diethyl ether, for example. You could also have THF. That's another common ether that we use. And then in this solution, we throw in a suspension of magnesium, elemental magnesium. That little knot there, that means it's got a zero charge on it. I often think about elemental magnesium. So elemental magnesium in a suspension with some of this diethyl ether. And so you throw it in there with this suspension, and here's what happens. Well, he loses his charge. Goodbye. Okay, so we're here. He loses his no charge symbol. He's here. In a suspension, and it's basically like, I don't know if you've ever been on like a two-person couch with two people on it, and then there comes in this third person and he's like, hey, can I sit on the couch in between you two? And you're like, no, this is a two-person couch and we're already here. And he keeps coming closer and closer, and you're like, literally, dude, I said no. You cannot join us on the couch. And so he's like, basically like, I don't care. So he comes in here and he just intercalates that bond. That's basically what magnesium does. Magnesium is like, I see a nice polar covalent bond that I just want to put myself in the middle of. And he just does that very literally in between carbon and bromine. Puts himself in the middle. Now, a couple of things happen when this happens. One thing that happens is our bats, aka our ether, come and surround our ethyl magnesium bromide, and they form this thing called coordination bonds. So coordination bonds are just really there for stabilizing this weird coordinate right now. And the reason they have to stabilize it so much is this is actually quite unstable, because now I have this partial negative charge on the carbon, which is pretty new for us, and a partial plus on this magnesium. So the partial negative on the carbon means a couple of things. First of all, it means that we have a carbon nucleophile. We haven't really seen a carbon nucleophile before. Looking at this, thinking about a carbon nucleophile, if I have a carbon nucleophile, I could have a carbon electrophile. I could make new carbon-carbon bonds, and that's super important for us. We also need to think about how this actually matters when we're thinking about stability of these things. So maybe having something that is primary with a partial negative is going to be a little bit better than something that is tertiary, just because of the induction and hyperconjugation of surrounding sp3 hybridized atoms. But really what we super concern ourselves with is the fact that we can make new carbon-carbon bonds under this system. Now, similarly, lithium is kind of similar to that. Lithium, we're going to ignore this part. Lithium kind of comes in, there's maybe a couple of lithiums there, and he's like, okay, excuse me, I'm here now. And then the bromine, Br minus, is off doing his own thing. And maybe I have another Li plus that's there as well. These don't really need to be stabilized in the same way that we stabilize a Grignard with the ether. We usually have some kind of alkane, maybe hexane, pentane, something like that, that's in there. Now what we do need to remember here is that the carbon is the nucleophile, which means that the electrons belong, and that's the electrons in this bond, the CLI bond right here. The electrons in this bond in particular belong to carbon. And so it would be appropriate to draw this. This is the same as this. It would be appropriate to draw it this way. This is showing it as a covalent bond, and this is showing it in its ionic bond form. So there's some weird things that are going on there. But let's just look at a general gist of what goes on in a Grignard reaction. So, like we mentioned before, and this is the same for an organolithium as well. Let's just keep on keeping on with the ethyl magnesium bromide. What happens is, we mentioned before, this is partial negative and this is partial plus. This being partial negative means I have a carbon nucleophile. If I reacted this with a general ketone or aldehyde, so some kind of carbonyl that does not have reactive groups on either side, not reactive to a carbonyl, Grignard in specific, what will happen is, now, okay, here's another thing. Your textbook is evil in the sense that it will show you moving this over, or this attacking the magnesium. That's just doing too much. What you need to be concerned with in the mechanism is that you need to show the electrons in this bond in particular. The electrons in this bond in particular, because they belong to this carbon, come over here and attack the carbonyl right here, because this carbon is a good electrophile. So that carbon is a good electrophile, and we push these electrons up onto that oxygen. And so when we do that, we're going to make a new carbon-carbon bond. So this is going to have this here. And now you can also show the MgBr plus as an ionic bond here. You can show this happening and show it next to each other. I think it's doing too much to show this coming over here and attacking that. I'm gonna say, I think your book does that for maybe the sake of you understanding it, that, you know, it comes and forms a weird ionic complex next to it. You don't need to show it in a mechanism. It's not important. I think it adds too much confusion. And basically the same thing happens if we did the same exact thing with a lithium. So maybe we do the same thing. You don't need to know too much. You just need to know the electrons are coming from this CLI bond because the carbon owns those electrons. It's more electron negative than the lithium. So that is the basic bare bones of what happens with organometallics. Carbon nucleophile attacks carbon electrophile. There's a couple more examples of carbon electrophiles though. So we're not quite done looking at examples of carbon electrophiles, and so I wanted to go through this list here and look at what some of them are, and then maybe look at the general gist of what happens here. So I'm just going to say our MgBr. Remember, when we're here with this, we need to put some kind of ether in there. This is going to come over and attack this carbon of the epoxide. Epoxides, one, they're not very stable because they're a three-membered ring. We have those banana bonds, remember? And it's connected, it's a carbon connected to an oxygen that could be a good leaving group. And so this is an excellent electrophile. Nucleophile attacks the electrophile. Also, it attacks the less substituted side. Why does it attack the less substituted side? Maybe you could think about why that might attack the less substituted side. We can talk about that later. Anywhoosie, this is going to attack the less substituted side for a reason that we'll talk about, I don't know, in our Zoom recitations or something. O minus. And now my R group has connected there. I want to make sure I count my carbons. 1, 2, 3. 1, 2, 3. Yep, the same number of carbons were there originally. I got my R and I have my O minus. Now notice how stereochemistry maintained itself. Now, we're not done yet because I have to get through all of my first reaction before I can move on to my second reaction. What I left out over here is this is not our final product that we're probably looking for. Probably the product that we're looking for looks something like this. Probably an alcohol. We need to have an aqueous acid workup step in order to get there. We need a workup step. What exactly is that workup step? The workup step is adding HCl and water, or maybe H2SO4 and water, or something like that. That's just going to do an acid-base proton transfer here, so we end up with a final product that's an alcohol, which is generally what we're looking for. So in both of these cases, after the first and the second step has completed, we're going to end up with this secondary alcohol. What about this one? Let's just try this out. Carbon nucleophile attacks the carbon electrophile, and we kick this up. Now this is getting a little bit advanced, and maybe this is a little bit more towards the stuff you're going to learn next semester. But we make this thing called a tetrahedral intermediate. Oh my goodness. Wonderful. And R's there. I have a leaving group here, and I did not specify what the leaving group is, although I do know that it's not going to be OH, because OH is not a good leaving group from a carbonyl. It's not a good leaving group from a carbonyl. But it could be, I don't know, a halogen, or this could be instead maybe an ester or something like that with an OR group. So these electrons can come back down, reform the carbonyl, and kick off my leaving group. I'm just going to say excess. I didn't really specify excess. But you gotta always assume for Grignards that what we're working with is in excess. Oh my goodness, I did it again. I got my leaving group to leave. Now what do I have? Well, this looks a lot like a ketone. So this ketone can react again with another molecule of my Grignard. Whether I specified excess or not, I gotta go all the way through the first step until I have literally nothing left. Sorry, that's a different problem. Until I literally have nothing left to do. And then I'm going to end up with this, which after my aqueous acid workup step, I just end up with the tertiary alcohol. And this is going to give me the same exact product. So the next thing is I have this carboxylic acid. Now let's say we reacted my Grignard with a carboxylic acid. What's going to happen? You probably correctly guessed it. I'm going to end up with this, O minus. Same deal if I reacted with RLI. This is a really good, not just is it a good nucleophile, it's a strong base as well. And so it's going to grab that proton, put the electrons between O and H back onto the oxygen. So now I have this carboxylate. So this is the first time where we have deviated from organolithium and Grignard doing the same thing. Here and here they did the same thing. Here and here they did the same thing. In this case, this is as good as it's going to get. It's not going to react any further. If I want to do anything with it, I'm just going to have to use the aqueous acid workup step in step 2 to turn it back into a carboxylic acid. I've turned it back into the carboxylic acid. So it will almost in effect do no reaction, although you can't put no reaction because technically it reacted. It just stayed turned back into the same thing that we started with. Here, it's so weird. Organolithiums are stronger than Grignard reagents in that they can react a second time with this. They are so strong that they can come in and attack this bond, this carbon, take this bond up, and I can make this weird dianion, which doesn't look pleasant. Now, once we get to this point, it can't react any further. We've gotten all the way through the first step before we move on to the second step. After the second step, what are we going to do? We're going to make the hydrate. We know a little bit about hydrates. We talked about them in the last video where we talked about oxidation. And we know that whenever we have a hydrate, it will rapidly equilibrate back into the it'll rapidly equilibrate back into the ketone. So this is the first one where we react the same thing with a Grignard versus an organolithium and get two different products out. This is a little bit advanced. We haven't really talked about this yet, and it's mostly second semester, but it's kind of cool material. A couple of more things. One more thing that we can look at is what happens when we do the same thing, but instead with nitriles. So in this case, first step of the reaction, our MgBr, comes in and attacks this nitrile right here and kicks this up. N minus. Maybe we still have my MgBr counter ion hanging out nearby. We can't do anything else to this. This is as far as this reaction will take us. Then in the second step, we end up, when we do HCl with water, we end up turning this into the ketone, which this is complicated, confusing. We aren't really going to talk about this in 2510, but it is cool reactions. So these go to make the same thing. And the last one, this one's actually quite cool for synthesis. Let's just say we have our MgBr, because you know, we have had that the whole time. This can attack a carbonyl. We've already talked about this. This is a carbonyl, carbon dioxide, CO2. It's a very fancy carbonyl that has two double bonds to oxygen on either side, but we can attack this carbonyl, break one of them, it doesn't actually matter which one we break, and we can end up with something cool. What's this look like? This looks like the product of this first step right here, which we said we could not react any further when we're working with a Grignard. And so the second step, when we add water and HCl, we're just going to end up making a carboxylic acid. So this is a quick and easy way to make carboxylic acids using a Grignard. We just react it with CO2 instead. Same deal if we reacted RLI. This can come and attack CO2 and break that one of those double bonds there. This could potentially react again. We've seen this already before when we were looking at this last example. This could come in and attack this carboxylate again, which is wonderful. We'll make that dianion, which will turn into a hydrate in step 2, which never actually stays in the form of a hydrate because it rapidly equilibrates into the ketone. Forgot to draw my R's. So there's a lot of really cool things you can do with organolithiums, but they're very important for synthesis in specific because they're a really cool and handy way of making new carbon-carbon bonds. And all we need to do is generate them and then put a carbon electrophile in there and we're good to go. But yeah, I look forward to hearing from you guys. Let me know if you have any questions, and we'll talk more later.